Hello, once again. As I mentioned before, I'm going to continue with where we stopped. We looked at an introduction to second-order linear differential equations, um, and then we did some examples after showing how you actually solve the homogeneous differential equations. Okay, so we'll look at some existence and uniqueness theorems of homogeneous equations. That's what we're going to do here. Okay, so the first theorem we want to look at is theorem 6 here for any real number, or for real numbers a, b, c, t naught, y naught, and y1. There exists a unique solution to the IVP. All right, this is the homogeneous equation, and the initial conditions are given by this: y at t naught is capital Y naught, y prime at t naught is capital Y1, and the solution is valid for all t. All right, for all real numbers. Okay. So this is a general existence and uniqueness theorem for homogeneous equations. So this tells us that if we have a homogeneous equation with initial conditions, there is a solution to the equation, and that solution is unique. All right, uniqueness is based on these guys. So we are going to go through this assuming that we have a solution. In actual fact, we'll prove some theorems. So we're not going to prove this one here. Once we look at higher order differential equations and systems of equations, it will be straightforward to prove this, okay, to prove this one. But we'll look at some existence and some representation theorems, okay, that are important for studying homogeneous equations. Okay, so that's what we're going to do. Now, note that, and this is very important, if y of t and y prime vanish, okay, simultaneously at a point, let's say t naught, okay, that is at t naught, y naught is 0 and y1 is also 0. If this is 0 and this is also 0 for the homogeneous equation, then the only solution to the differential equation, to the homogeneous differential equation, is the identically 0 solution. Okay, so keep this in mind. This is very important. It will become very important when we look at some of the other theorems and lemmas. Okay, so if you have a homogeneous equation and the initial conditions are such that at a point this guy is 0 and this is also 0, then the only solution that is satisfied by this equation is the identically 0 solution. It is 0 everywhere. Okay. Secondly, we want to apply this existence and uniqueness theorems to show that if I have two solutions, let's say y1 and y2, okay, of the homogeneous equation, then we can always find the constant C1 and C2 such that this linear combination here will meet, you know, this specific or special initial conditions in 12. And therefore, it is a unique solution to the IVP. Okay. So if I have two solutions, y1 and y2, and I form this linear combination, we want to be able to use this theorem to show that I can always find this C1 and C2, the constant, to satisfy these initial conditions. And if I can find C1 and C2 to satisfy these initial conditions, then the solution, the combination of solutions, right, y1 plus y2, this combination here is actually the unique solution. All right. But before we do that, we need to be a little more precise, all right, in the sense that we can't just take any solutions y1 and y2 and combine them and say that they will meet specific conditions, all right? And we'll see why that is important. So we actually have to pick the solutions, the two solutions, y1 and y2, they have to meet certain criteria, a certain criteria. And that is called linear independence, okay? Or we have linearly independent solutions. They have to meet that criteria. We'll define that very soon. And once they meet that criteria, then we can be sure that when we combine them, okay, when we combine them, then C1 and C2 will actually meet that initial conditions to get a unique solution, okay? So you can't just pick any two solutions. This is because, for instance, if I have a solution y2, okay, and I have another solution y1, and y2 is a constant multiple of y1. For instance, if y2 is equal to some constant d times y1, then what that means is that if I plug in those solutions into this linear combination here, okay, C1, y1 plus C2, y2, what I'm going to get is going to be some other constant multiplied by y1. Okay. In other words, I've reduced the general solution to this solution here. Okay. Now this solution here has only one constant, but the IVP has two conditions. So I don't expect just a single constant to satisfy those two conditions. Okay. And so if I have a solution if I have two solutions and they are dependent on each other, one is a linear combination of the other one, or sorry, one is a constant multiple of the other solution, then I can't use those two solutions to form a combination. Otherwise, they will not satisfy the two conditions there. Okay, so that is why it is important to put a criteria on the type of solutions that you can combine. Okay, in the same way, if, for instance, one of the solutions is 0 and the other is not, then again, they are linearly dependent on each other. Okay, so one is a multiple of the other one, because I can take 0 times whatever y1 is, I'm still going to get a 0. So y2 depends on y1 some way. Okay, good. So we need to define what we mean by linear independence. Okay, and then we'll come back to this theorem. Okay, so here's a definition for linear independence of two functions. Okay, so this is important for differential equations. A pair of functions y1 and y2 is said to be linearly independent on an interval I if and only if neither of them is a constant multiple of the other on the interval. We say that y1 and y2 are linearly dependent on the interval if one of them is a constant multiple. That multiple can be 0, all right? That constant multiple we are talking about here can be 0 of the other one, okay? So we'll look at two examples of solutions that are linearly independent, and then two of those that are linearly dependent, just to make this clearer. Okay, so consider the interval I. This can be any interval actually for these examples. The functions y1, e to the t, and y2, which is t times e to the t, are linearly independent. Okay, on this, actually on the whole real line. Okay, since neither of them is a constant multiple of the other one, right? For instance, y1 here is equal to, I have t times y2, right? Actually is the opposite here. This should have been y2. y2 is equal to t times y1. Okay, so that should have been, in any case, you cannot take a constant, multiply by one of them to get the other one. Okay, so none of them is a constant multiple of the other one. Because of that, these two functions are linearly independent. Okay, the same way, e to the negative 3t and e to the 4t are linearly independent. None of them is a multiple of the other, a constant multiple of the other one. Note that we can actually write y1 to be equal to e to the negative 7t times e to the 4t, which is e to the negative 70 times y2, all right? So, and this guy here is not a constant, all right? It's not a constant, therefore, none is a constant multiple of the other one. Okay, so these are just two examples of linearly independent functions. We'll look at theorems that actually tells you how you can test, right? How you can test to check that given functions are linearly dependent or independent. We'll look at that general case later. We'll look at these two examples also. Y1 is cosine of 2t, all right? And then we have y2, which is 5 cos squared t minus 5 sine squared t. These functions, y1 and y2 here, are linearly dependent. They depend on each other. Why? Because I can actually expand this guy, cos 2t, and I can write it as cos squared t minus sine squared t. But this is the same as 1 over 5 multiplied by y2. Okay? Or if you like, y2 is equal to 5 times y1. So one of them is a constant multiple. You have a constant multiplied by the other one. Same here, you have a constant 1 over 5 multiplied by the other one. Therefore, these are dependent. They are linearly dependent. Okay? In the same way, the function e to the 2t and 0, they are also linearly dependent because I can write y2 to be 0 times y1. Okay? So I have a constant multiplied by the other one. The constant here is 0. Okay, therefore y2 is a constant multiple of y1. And so this and that, all right, are also linearly dependent. So these are just examples to illustrate linear dependence and linear independence. Good. Now we'll get to the this theorem. Okay. Let's see. So we came from here, and I said this will not prove later on. We want to look at this representation of solutions to IVPs. Okay, the fact that I can actually form a linear combination of solutions if I have two linear independent solutions. So that's what we want to look at. And then we'll prove this. All right, we'll prove this after we have proved a lemma. Okay, but let's state this one here. If y1 and y2 are two solutions to the differential equation 8, that's the homogeneous differential equation, that are linearly independent. So now we have specified that these solutions have to be linearly independent on an interval containing your initial condition, your initial point, actually T0. Then this is that you can always find constant, unique constant C1 and C2 that will always be found, so that this combination here satisfies your IVP 12 on the interval. The IVP is the theorem we showed before, this one here, this one. Okay, this is the IVP that we are looking at. So we have two linearly independent solutions to the IVP. Then I can always show that this, I can always combine them to show that C1 and C2 can be found, all right? And they can be found that satisfy the initial condition at T0, okay? Good. So now, how do we prove this? To make the proof of this easier, we actually want to go back and want to actually prove a lemma. And once we prove that lemma, it will be much easier to prove this one. So we'll look at this lemma called, it is often called the technical lemma, okay? So we'll state the technical lemma, prove it, and then once we have proved the technical lemma, we'll go back and prove this theorem 10 here, the representation of solutions. And that'll bring us to the end of this, this particular session, okay? So condition for linear dependence of solutions. Okay, so we're going to state a condition that tells you that when that condition is satisfied, it shows that the two solutions are linearly dependent on each other. Okay, so for any real numbers A, B, C, if y1 and y2 are any two solutions to the differential equation 8, that's a homogeneous equation on an interval, a whole real line, and if this equality holds, okay, at some point, note that tau here is a point, it's a number. It's not T. Tau is a number like T0. Okay, so if this holds at some point tau of the interval I, then your two solutions y1 and y2 are linearly dependent on the whole interval. Okay, now this expression here on the left-hand side here, this is called the Wronskian. I don't know if you heard about the Wronskian before, I'm sure. Okay, so that is the Wronskian. So this says that if the Wronskian at any point of the interval is 0, then the two solutions y1 and y2 are dependent, are linearly dependent on each other. Okay, so we want to prove that. The approach we are going to use is that we want to, if they are dependent, for instance, then we can always say that y2 is equal to some constant times y1. So we're going to pick a couple of conditions, all right, a couple of cases. So give a condition on y1 and show that with that condition, y2 is a constant times y1. And therefore, they are linearly dependent. And then set up another condition on y1 and show that even with that, they are dependent. We'll do that for 3 cases, and that will bring us to the end of that proof. Okay, so that's the plan for the proof. So the condition we are given is this: the Wronskian at tau, or the number tau, is equal to 0. We can rearrange this to write it as this from here. Okay, because tau here is a number, the left-hand side and right-hand side are just some constants. So let's just say this is equal to some alpha. Okay, good. So we're going to look at, this is what I just explained here. So I'm going to write y2. We're going to show that y2 is equal to some alpha times y1. And if this is the case, all right, then of course, y2 is a constant multiple of y1, therefore they are linearly dependent. So we're going to show this for different cases. So for case one, let's assume that y1 of tau is not 0, okay? If y1 of tau is not 0, then of course this is not infinite. This is some real number, right? Which is, let's call this alpha, okay? So if y1 at tau is not 0, we can let alpha be equal to y2 over y1, which is this, okay? And then we consider the solution to the homogeneous equation to be equal to yt. Note that y1 of t is already a solution, all right? So I'm going to consider another solution, which is just a constant times y1. Okay, if y1 is a solution, then the constant times y1 is also a solution, okay? Good, from what we explained previously. Okay, but I'm going to show, okay, the idea for the proof is to show that this y here, which is alpha times y1, is actually y2, okay? And if it's y2, then of course, y2 and y1 are linearly dependent because one is a constant multiple of the other one, okay? Good. And how we show that y is actually y2 is that we are going to show that y here and at tau and the derivative of y at tau are the same as y2 and then the derivative of y2 at tau. Because of that and because of uniqueness, they have to be the same functions. Therefore, y and y2 are the same. And so y2 is equal to a constant times y1, therefore it's linear dependent. So that would be the plan for all the cases. Okay, so I'm not going to do too much talking again. I think I've explained enough. Let's go straight to this proof here. So I've chosen alpha to be this, and I've said let y to be a solution of the homogeneous equation as given by this. Okay, now at t equals tau, we're going to have y at tau, right? I'm going to plug tau here. Y at tau is equal to alpha y1 at tau, all right? But alpha is given by y2 over y1 at tau. So that is given by this multiplied by y tau. Y1 cancels y1. So this is just equal to y2 at tau. So y at tau is the same as y2 at tau, right? Or if you like, y2 at tau is the same as alpha times y1 tau. So that's the first point. The second one is that if I differentiate this, y prime at t is alpha y prime at t, right? And I can plug in tau. If I do that, I get y prime tau is equal to alpha y1 prime at tau. Again, alpha is y2 tau over y1 tau multiplied by this guy, which gives you this. Okay, great. But if you go back to this, or if you like this, then you see that y you can multiply. If you multiply this, multiply both sides by y1 prime, then you see that this guy here is actually y2 prime. All right, okay, multiply this by that, then y2 prime is equal to y1 prime at tau times this, which is this. So this is actually y2 prime. Okay, so y1 prime is equal to this, therefore y prime at tau is equal to y2 prime at tau. So we have shown that the y we chose as a solution, that y here at the point tau is the same as y2. The derivative of y at tau is also the same as y2 of tau. So by uniqueness, y2 has to be the same function as alpha y1 tau on I. And if they are the same, then of course they are linearly dependent on each other, right? y2 is equal to alpha y1, so they are dependent. So with the first case, we have shown that y1 and y2 are linearly dependent, okay? Then we'll look at the second case and follow a similar train of thought. Case 2, we are going to assume that in this case, y1 is 0, okay? But y1 prime is not 0, okay? If y1 is 0, we will show that y2 at tau is also 0. We will show that shortly. Okay, so y1 prime is not 0. So we can go, if you go back here, y1 prime is not 0. So we can let our alpha be equal to this guy here, right? Alpha now is y2 prime over y1 prime, okay? Which is what I've written here. So again, we are going to show that the function y of t, which is a solution, alpha times y1 t, satisfy the same condition at tau as y2. So if I plug in tau here, I'm going to have y tau is equal to alpha. My alpha now is this multiplied by y1 at tau. Okay. Now y1 at tau we said is 0, right? This under this condition, condition 2 or case 2, y1 at tau is 0. Therefore, this is equal to 0. All right. All right. This is 0. And that is equal to y2 at what? At tau. Okay. All right. So we have this condition that shows that both y1 y at tau is 0 and y2 at tau is 0 as well. Showing that y2 at tau is 0 is easy to show, right? If y1 is 0, if you go back to this condition, if y1 is 0, this guy is 0, right? This guy here, y1 prime is not 0, so I can divide through by 8, and then I get y2 at tau is 0. So that is how we get y2 at tau is 0. So here we have shown that y at tau is 0 and y2 at tau is also 0. The next thing we're going to show that the derivatives are also 0. And so by uniqueness, they have to be the same functions. That's the plan. So find the derivative of this and plug in tau. That gives you y prime at tau is equal to, note that alpha is this. So I put it there. Y1 prime is this. Now y1 prime cancels y1 prime. And so this is just equal to y2 prime at tau. So again, the derivative of y at tau is the same as the derivative of y2 at tau. And so by uniqueness, again, y2 has to be equal to alpha times y1t. Therefore, they are linearly dependent. So in case 1 and case 2, we have shown that or if you like, y1 and y2 are linearly dependent. The final case that we want to look at is the case where both of them are 0, right? First, we assume this is not 0. Okay, so in the next case, we want to show what happens. Excuse me. We want to show what happens if y1 is 0 and y prime is also 0. Okay, in that case, what happens is that if this is 0, we are then showing that y1t is a solution to the homogeneous equation. Of course, that is the premise. Y1 and Y2 are solutions to 8. Okay, this is a solution to 8, and that is satisfying the initial condition y1 at tau is equal to y1 prime at tau equals 0. Okay, so you have a solution to the homogeneous equation, and the initial conditions is the 0 conditions. Remember that we said that if you have the homogeneous equation and the initial conditions are all 0, then the only solution to that homogeneous equation is the identically 0 solution. Okay? Okay, so if y1 is a solution, weight these conditions, then the solution is actually the identically 0 solution. All right? Okay? Okay, so, but the identical 0 solution is a unique solution. Yeah, that's why is a solution to such an initial value problem. Therefore, y1t is identically 0 and can also be written as 0 times y2, right? Which means that y1 and y2 again are linearly dependent solutions. So in all 3 cases, case 1, case 2, and case 3, we have demonstrated that y1 and y2 are linearly dependent on each other, and therefore, if that condition, if the Wronskian at a point tau is equal to 0, then the 2 solutions y1 and y2 are linearly dependent on each other. Okay, good. So now that we have proved this so-called technical lemma, it becomes easier now to go back and prove theorem 10, okay, which is the so-called representation theorem. I'm going to repeat it here before we prove it. So here, so now that we have proved this technical lemma, we can now prove this. This theorem said that if y1 and y2 are any 2 solutions to the differential equation 8, that is the homogeneous equation, that are linearly independent, this is important, okay, on an interval I containing a point t0, the unique constants C1 and C2 can always be found so that this linear combination here satisfies the IVP 12. The IVP is given by this, okay, on the interval I. Okay, so our point here is that we already know that this, okay, this combination here satisfies that. That is not the problem. It's easy to show that. You can plug this in and show that this satisfies this. The main proof is to show that I can actually choose, or I can obtain this C1 and C2 such that, okay, this combination here is a solution, and therefore it's a unique solution to that. Okay. Okay, so how do we prove that? The technical lemma once again will help us to do that. So we're going to, this is a solution. If this is a solution to this equation, then y is equal to this. So I can plug in t naught, and I can also find the derivative of it, and then plug in t naught, and it should equal to y1, right? If I put t naught, it should equal to big Y0, and then if I find the derivative and plug in t naught, it should be equal to big Y at 1, right? So that's what we're going to do. So since this is a solution, we have these two equations here, okay? So basically, I just solved these two equations for the two unknowns C1 and C2, and I get these expressions here. Okay, so this is just linear. You can solve them simultaneously to get that. Now, this is okay as long as the denominators are not 0, right? If the denominators go to 0, then of course, this thing blows up and we can't get any real C1 and C2. But the technical lemma tells us that, okay, since y1 and y2 are linearly independent, then this expression here in the denominator never goes to 0, okay? This never goes to 0 from the technical lemma. And since this is never 0, then we are assured that we have C1 and C2, which can be chosen to satisfy the initial condition at T naught. Okay, so that is basically the proof. So we have really proved that theorem 10 here. Okay, by using the technical lemma. And the crust of this is that these solutions here, y1 and y2, have to be what? They have to be linearly independent. Once they are linearly independent, then you are sure that this linear combination will satisfy these given conditions on the interval I. Okay, good. So if you are wondering about this, right, how this technical lemma is applied here, the next slide is a reformulation of the technical lemma. Remember, the technical lemma says that if the Wronskian is equal to 0 at a point, then the two functions are linearly dependent. Okay, a reformulation of that lemma is given by this. Okay, which is an exercise. You can look at it. It says that let y1 and y2 be a pair of solutions to the homogeneous equation. All right, on an interval I. Then these two solutions, y1 and y2, are linearly independent on the interval if and only if. Remember, the technical lemma goes in only one direction. This one is if and only if the Wronskian is not equal to 0. So if I have two solutions, y1 and y2, and I find the Wronskian and the Wronskian is not equal to 0, then the two solutions are linearly dependent. On the other hand, if the two solutions are linearly independent, then the Wronskian never goes to 0. All right, so that is actually the one we applied finally here. All right, because y1 and y2 are linear independence, this denominator never goes to 0. And so we are sure of getting C1 and C2. Okay, so I leave the proof as an exercise as written here. Okay, so the proof of, as I said before, of the main existence and uniqueness theorem for second order equations is much easier to prove after we've looked at higher order equations and systems of equations. Then we can just apply the theorem for systems, because if you have a higher order equation or second order equation, you can write it as a system. And so we can apply the theorem for uniqueness and existence for systems to the higher order equations, and for that matter, for second order equations. And so it's much easier that way. So we'll come back to that later on. Okay. So I will end this video here. The next video will look at non-homogeneous equations, and we'll cover these 4 points. Okay. All right. So I'll see you later on. In my next video is going to start covering non-homogeneous equations. Okay.